Now, I don't know how many of you know, but today is Ada Lovelace Day. And when I was thinking of a topic to start my series with, I thought it would be very good to talk about some of the work related to the work of Ada Lovelace, one of the pioneers of modern computing. It also happens to be my own subject, which is kind of nice as well. So I'm going to talk today about the mathematics of future computing. But I'm also going to tell you about the mathematics of computing in the past as well. So we'll get a little bit of a history, and then we'll look forward into the 21st century and maybe beyond. So you may be all asking yourselves, what's a professor of geometry doing talking about computing? Surely a talk about computing should be given by the professor of IT. And my answer to that is absolutely the professor of IT should talk about computing. Computing is now impacting our lives in innumerable ways. Probably all of you have access to a computer in some form, either through a laptop or through a machine like a cash machine or a smartphone or even a washing machine which has a computer built into it. But computers, as such, have not always been in the home, and I will claim that computers were originally invented by mathematicians, and they were invented to solve mathematical and logical problems. And even though computers are very much now part of our domestic environment, it's mathematics which lies at the heart of all of the algorithms that computers use, and also at the heart of the algorithms they will use in the future. So that is my motivation for giving this talk as Professor of Geometry. So let me introduce you to this guy. This is Professor Moore. And he came up with a rule in the 1960s, which has proved remarkably accurate, which was that computer hardware power doubles every 18 months. Okay. And this is very true. The first computers, I wrote my first computer program when I was 11 in 1971 on a very, very primitive machine compared with what we've got nowadays. And this graph shows the power of a computer measured in number of transistors on a chip. This is a logarithmic scale, so it's going up in factors of 10 over the last 50 or so years since Moore's prediction for various different types of computers. So this is kind of where we are now. And Moore's law has proved very accurate. So this is showing that computer power increases with the amount of hardware. But maybe you don't realize that an even greater speed up has happened because of the work of mathematicians. I'd like to say mathematicians such as myself, because this is my own research area. And this shows in the same sort of time the speed up that we've had as new mathematical algorithms have come online to solve problems. These are mathematical algorithms particularly to solve what we call linear systems, which lie at the heart of big computations. And these things here were early algorithms like the Gauss-Seidel algorithm, but the thing up here, multigrid, or MG, which is the algorithms we're now developing for the Met Office. And you can see we've had a speed up which is actually greater than Moore's law in algorithms, and that combined with the speed up in hardware has led to the computing power that we have today. So this is the thrust of my talk. We are seeing huge changes already. We're going to see even greater changes to come as we see much faster computers, a huge increase in the amount of data that we have, the role of learning in machines, which is a tsunami about to hit us, and I'll touch also on quantum computing. And the only way to make sense of this scale and to see into the future is to use mathematics. And here I have a lovely quote from one of the CEOs of Boeing, which makes a lot of use of computing power, that says taking full advantage of computing tools requires more mathematical sophistication, not less. So I'm now going to take you on a journey, as I say, through the history of computing up to the present day, and I'm going to show you how we can look into the future and a little bit of the role that mathematics plays in that. So I want to show you a picture now of the first ever digital computer. There it is. So that's the earliest digital computer. Mathematics did not start as an abstract concept. It started using computing tools, and we used our fingers. Why do we know that? Because we count in base 10 and we have 10 fingers. This cannot be a coincidence. Okay, so we know for a fact that the earliest computations were made using an excellent digital device. It's nice because you can, not only can you compute on it, it's got memory as well. Okay, unless you cut your fingers off. Okay, so that's the earliest digital computer. Here is another example of early computer. This is a tally stick, which was found in a cave. It's approximately 5,000 years old, and it's clear that our ancestors then were doing computations recorded on that. And another very useful and still in use computer was the abacus, which was used in ancient times and is still in use today. This is the international abacus competition held in Japan, where the entrants were asked to do a computation which ended up with an 8-digit answer. So the abacus is still pretty efficient for doing certain computations. But one of the big advances in computing occurred in the 17th century when Napier, who was a Scottish mathematician, came up with the idea of using logarithms as a way of doing computation. Now, I am sufficiently old, and I imagine looking at the audience, some of you are of a similar vintage, to have used logarithms when you were at school. I hope that isn't too insulting to my audience. And the idea of logarithms was invented by Napier. Much to my delight, when I was doing the research for this talk and went onto Wikipedia, I discovered it referred to Gresham College. And it said here in Wikipedia, his invention of logarithms was quickly taken up at Gresham College. I assume by the professor of geometry, maybe the professor of astronomy as well. And it doesn't then say what that person then did, but it's nice that Gresham gets a mention. And they talk then about Henry Briggs, prominent English mathematician who played an equally significant role in the history of logarithms. So how do we use logarithms to compute? Well, the idea of logarithms is that if you have a number x, then its logarithm to base 10 is the number a, which is the number which, when you raise 10 to that number, gives you x. So if x is 100, 100 is 10 squared, that's 10 to the power of 2, so the logarithm of 100 is 2, the logarithm of 10 is 1, the logarithm of 1,000 is 3, the logarithm of 2 is 0.30103, etc., etc. And Napier realized that if he computed these things here, then he could use these as a way of speeding up computations. And the reason for that was the law of exponents. The law of exponents was that if you take x and y as two numbers with logarithms a and b, and you multiply them, then you get 10 to the a times 10 to the b, and the law of exponents says that that's 10 to the a plus b. In other words, the logarithm of x times y is the sum of the logarithm of x and the logarithm of y. So if you want to work out x, y, what you do is you find the logarithms, you add them up, and then you invert that process, finding the anti-logarithm, and that tells you what x, y is. You can do exactly the same with division. X divided by y is 10 to the a over 10 to the b is 10 to the a minus b, and that gives you the division again as a subtraction. And division is actually quite hard to do by hand, and this shows you that it's equivalent to subtraction. So this was a major breakthrough. And all you have to do is to work out the logarithms in advance. But this could be done, and they could be tabulated. They were done at the time by computers, and a computer at that time was a room full of students working away to calculate these numbers. And here is a table of logarithms. There's the number, there's its logarithm. So the number 1 has logarithm 0. The number 1.09 has logarithm 0.03743. And here, that's the number 1.001 and so on. And what you had to do when I was at school was get very fast finding a number and finding its logarithm and doing all the corrections. It took a while, but it was worth it. And to give you an example, suppose you want to work out 13.45 times 23.46. The logarithm of 13.45 is 1.1287. 23.56 is 1.3722. You add these together. That doesn't take very long. You take the antilog of this, and it's 316.9. And that is close enough to 316.882 for many purposes. And it takes a lot less time to calculate. So this became very popular, and certainly when I was at school up to the age of 16, I'll tell you what happened when I got to 16, this was how we calculated products and divisions. Later on, it was realized that you could automate this process using a slide rule. Quick show of hands, who here used a slide rule? Okay, lots of us did. I love slide rules. They have a kind of nice mechanical analog feel to them. And the way a slide rule works is that each of these scales is constructed so that if you have a number on that scale, the position it is on that scale is proportional to its logarithm. And by moving the scales around, you end up adding logarithms, and that's equivalent to multiplying the numbers. So slide rules was simply a mechanical way of adding logarithms together. This is my own slide rule. There we are. And I've set it up to do exactly the calculation I did there, to give 316.22. There you can just about see it. It's not particularly accurate, but again, it was good enough for calculations, and certainly the Spitfire was, for example, designed using a slide rule. So slide rules and logarithms were great fun, and I still maintain they're very useful. If you're going shopping and you want to compare prices against amount, then if you set them up on a slide rule, you can simultaneously compare a lot of prices once against each other, and that's very useful. However, slide rules and logarithms have two big disadvantages. One is that they're quite slow, and secondly, you can't do repeated calculations quickly as a result. So whilst they're fun to use, they're not particularly accurate, and they're not really good for lots of calculations. So it was realized that to make progress in computation, you have to use some sort of mechanical process so you can do many calculations and possibly store the calculations as you go forward. And that led to the invention of mechanical computers. Now, my predecessor by some way, Professor Christopher Zeeman, was fascinated by mechanical computers and gave a wonderful lecture called Gears from the Greeks about this, which is the Antikythera, which was the very first mechanical computer to be known about, which was discovered at the bottom of the sea. It was a Greek computer, and it was used to calculate the motions of the planets and stars and calculate eclipses, and was incredibly accurate for the time. And as I say, that's over 2,000 years old. So we know that mechanical computers are at least that old. This computer here was developed in the 18th century by Pascal, and was basically an adding machine where you turned cogwheels and they added things together, and it's the predecessor for the Brunswiga mechanical computer, which again I used to use at school. But one of the great breakthroughs in mechanical computing came in the 19th century with Babbage. And Babbage naturally leads on to Ada Lovelace, so I want to spend a little bit of time talking about Babbage. So Babbage wanted to compute the results of formulae. Why did he want to do this? Well, one of the key things going on at the time was navigation. People needed tables for positions of the sun and the planets, and that required doing calculations, and the calculations involve formulae. They generally involve formulae using sines and cosines, but if you approximate these by polynomials, you can do the calculations using polynomials. This is a polynomial. Y is a function of x, in this case x squared and x cubed. And to calculate things like navigation tables, a lot of polynomials had to be evaluated. So Babbage, in the 19th century, put some thought into how you might calculate polynomials rapidly using a mechanical process. And he decided to exploit what's called the method of divided differences, which is generally accredited to Newton. So I want to tell you a bit about how that works and then how that led to Babbage's computer. So here is a polynomial here, and the line of numbers here are the values of this polynomial evaluated at different values of x. So if I put x equals 0 here, I get 1. If I put x equals 1, I get 1 plus 3 over 2 plus a half, which is 3. If I put x equals 2, I get 11. 3, I get 28. And 4, I get 57. So those are the values of the polynomial. I can now calculate the difference between these values. So if I take 3 minus 1, I get 2. 11 minus 3, I get 8. 28 minus 11 is 17. 57 minus 28 is 29. That's our first difference. If I calculate the next difference, that's the differences of the differences, I get 12, 9, and 6. I hope you can see how that works. And if you do it once again, you get 3 and 3. Now you might have noticed that those two numbers are the same. And that's not a coincidence. This is a cubic polynomial, and if you do this 4 times, you always get to a constant number for any cubic polynomial. If it was a quartic polynomial, so I had x to the 4th, I'd have to go one more line down. If it was a quadratic, I could do it with one less line. So I get this number here. Well, how do I then work out the next number up here? Well, I write the same number down again. There it is. I add 3 to 12, I get 15. I add 15 to 29, I get 44. I add 44 to 57, I get 101. And if you plug 5 into my polynomial, you get 101. So this allows me to work out this number without having to do any multiplications, just a ton of additions. If I want to work out the next one, I put a 3 there. 3 plus 15 is 18. 18 plus 44 is 62. 62 plus 101 is 163. And that's my polynomial when I put a 6 in. Easy. And that's what Babbage realized. This was a good way to calculate. Okay, so the method works for any polynomial, providing I take enough differences. If I take a function which is approximated by a polynomial, which is most functions, it continues to work pretty well. It's extremely mechanical. So in Babbage's time, these calculations were done by students or whatever turning a handle on a calculator. But if it's mechanical, it can be mechanized. This was the Industrial Revolution. Everything was being mechanized. Maybe calculations like this could be mechanized. So here's Babbage, one of the true fathers of the modern computer. And in 1823, he persuaded the government to give him £17,000, which I suppose would be more like £1 million now, a lot of money, to try to make a machine to do these calculations. And he went off to do this. Now, you might think, well, this is 200 years ago, whatever. What could that possibly mean nowadays? But actually, many of the problems that Babbage had to address to do this calculation are exactly the same sort of problems that we need to solve now in order to be able to compute accurately. So here are the problems he had to do. In order to add, he has to be able to represent what a number is. So if I have a number like a third, which is 0.33333333, and so on, somehow we need to be able to represent that in our computer in such a way we can do calculations with it. Okay. The more decimal digits that we have, the more accurate the calculation, but the slower the calculation and the harder it is to do. Secondly, you need to be able to store the numbers. If we go back to this table, we need to know all these numbers here to get that number there. So this has to be able to store at least 4 numbers. So we need to store the numbers. And thirdly, we need to be able to add the numbers together. Now, of course, Babbage didn't have access to any electronic calculator, so the only thing he could do was to do everything mechanically. And there's his difference machine. That's in the Science Museum now. This was one of his prototype machines, not the full version that he wanted to get working. But the way he decided to store numbers was as columns. So you'd have a column of cogwheels, and if you look on each cogwheel you can see a number, so you'd set the cogwheel in such a position such that each cogwheel would represent 1 decimal digit for a number. So that's a number there. And you can see we've got 1, 2, 3, 4, 5 different numbers there being stored. So each column stores a number, and the length of the column, the longer the column, the more accurate the number it is. And then you can add numbers together quite easily by literally turning the cogwheels. So you turn one cogwheel against another, and it adds, you just add the cogs together, and it turns and allows you to add numbers together. So the difference machine, which Babbage designed, was designed literally to add up the differences. So you'd set one number to be the 3, which is that constant number. That would then add to the next column to produce the next difference, add to the next column to produce the next difference, and so on until eventually you could calculate the result. Lovely idea, very mechanical, very straightforward, and basically a workable system. So Babbage built a prototype. His prototype had 3 columns, so he could store 3 numbers. Each column had 6 cogwheels, so he could store 3 numbers to 6 decimal places. And that allows him to do quadratic equations quite easily. Unfortunately, at this point, he either ran out of money or ran out of will or got interested in something else, which is probably more likely. I'll talk about that in a minute. And so he didn't go beyond the prototype stage. But if you go to the Science Museum, you can see a full-size machine based on Babbage's designs, which has 8 columns, so it can store 8 numbers of 31 wheels, so 8 numbers to 31 decimal places. So really very accurate. And you can see this in the Science Museum, and it works beautifully as a way of producing the solutions to these polynomials and therefore producing navigational tables. Lady Byron went to visit him. Lady Byron had a famous daughter, Ada Lovelace, we'll see her in a minute, and saw the prototype and said, "We both went to see the thinking machine." Well, so it seems last Monday, it raised several numbers to the 2nd and 3rd powers and extracted the root of a quadratic equation. So it did very well. But as I say, it was abandoned in 1842. Why did Babbage abandon it? Well, one reason, as often happens, is he got bored and wanted to do something better. He realized that the difference machine could only do one thing, which was to add up, and that wasn't particularly exciting. it would produce navigational tables, but he wanted to do a lot more. And so he started on the design of something much closer to the modern computer, what's called the analytical machine, analytical engine, and that's part of it. The analytical engine used the same idea of cogwheels and stuff to do much more. It also used punch cards, which were then being developed for the weaving industry, which you could use both to program and store things on. And that's a sort of schematic for it. So he designed a machine which was programmable, had an arithmetic unit, that was the bit which could add things up, controlled the flow, in other words, it could make decisions, do different things depending upon the results of calculations. It had memory, like its earlier predecessor, and you could program and put input using punch cards. So that's the analytical machine. Now, the analytical machine never really got going. The mechanical problems associated with it were too great, and even if it had worked, it would have been very, very slow. But still, the basic ideas were crucial to the final development of the computer. And this is where we get our hero for today, Ada Lovelace, who worked with Babbage on how to program the analytical machine to do various computations. And she was interested in these things. These are called Bernoulli numbers, which are the Taylor expansion of this thing here. These come up in all sorts of different contexts and are very useful things to calculate. And she wrote a program for the analytical engine to calculate this. And there it is. That is the world's first computer program. That is an incredibly important document, and as I say, that was developed by Ada Lovelace, who is often considered to be the world's first computer scientist, and she is honoured by having a computer language, Ada, named after her, and as I say, today is Ada Lovelace Day, so that's really good. Although sadly, she died rather young, having had quite an interesting life before then. If you want to learn more about Ada Lovelace, then my predecessor, Raymond Flood, gave a very nice Gresham lecture just about her. Well, let's move forward now, about 100 years. So Babbage was working on mechanical computers. I'll skip through to these. Now, in the 20th century, all our computers use electronics. We had to wait until the 20th century because modern electronics didn't really start until the invention of the thermionic valve at the beginning of the 20th century. So I want to take you through now the story of the modern electronic computer before we look at modern developments. So the invention of the modern computer started in the 1930s with people like Gödel and Turing looking at mathematical logic. It then had a huge stimulus in the Second World War associated with code breaking and the bomb. And then after the Second World War, that led to the first programmable computers. In the 1960s, with transistors and chips, we get the first commercial computers. And in the 1980s, we get the first practical home computers. And this is a picture of my first ever computer, which I bought in 1980, the immortal Acorn Atom. And I did my PhD on that, so it was quite a good piece of kit. Okay, so modern computing is generally associated with, I would say, three people in particular. Here are the first two, Alan Turing, who he died very young, committing suicide, we think, and Tommy Flowers, who lived rather longer. So these are the two kind of British pioneers of the modern electronic computer. And what are they most associated with? Well, they're primarily associated with the Colossus computer. So during the Second World War, the Germans were using a coding system called the Lorentz cipher. You may have heard of Enigma, which used cogwheels and mechanical devices. But the Lorentz cipher was a much more sophisticated system, largely based on teletype machines, and it was particularly important because Hitler was using the Lorentz cipher to send his most secret communications with. And a guy called Bill Tutt managed to work out, without even seeing it, how the Lorentz cipher worked in what's often considered one of the greatest intellectual achievements of the Second World War. Bill Tutt then went on to be one of the founding fathers of computer science in Canada. Knowing how the Lorentz cipher worked, Turing was able to come up with sort of mathematical process for then cracking that cipher. Now, I'm not going to go into any detail. That would be a complete different lecture. But it was obvious that the only way that that could be done was using some form of computer, and anything mechanical would be far too slow. So they then thought, well, the thing to do is to do it electronically. And this is where Tommy Flowers came in, because Tommy Flowers worked for the post office, and he was one of the inventors of the modern kind of electronic exchange for telephones and stuff like that. And so he used the ideas of the telephone exchange, which was based on electronics, to build the first computer. So he's as much a founder of this sort of computer as is Turing. And this is the Colossus computer, which was designed by Flowers using ideas from Turing and others to crack the Lorentz cipher. And you can see here two wrens operating it, and much of the input was using paper tape over here. And key to this was the thermionic valve, which was used to do all the operations. It's what we call semi-programmable, in that you would set up a switchboard to do various operations, but once you'd done that, it just went on and chunted away to do all the code breaking for that. So that's the Colossus. If you want to see it, you can't see the original. They were broken up after the war, but you can go to Bletchley Park and you can see a reconstruction of this, which is as true to the original as they could get. Now, Turing is very, very famous for his work on cracking the codes during the Second World War, but his impact on computer science and the development of the modern computer is much more profound than that. And what he is particularly famous for in the theoretical computer science community is the development of the first theoretical kind of computer that could do anything, which is called the Turing Machine. And every computer now is compared against the Turing Machine. And the idea of the Turing Machine was that you have a thing, a computer or whatever, which is in a certain state, and it can write onto a tape which moves past ahead, and it can write numbers onto that tape, and the tape can move backwards or forwards, and it will look at the numbers and will change its state according to those numbers and can write onto the tape as well. It might sound very simple, but Turing was able to prove that a computer which did this, which wrote onto a tape and changed its state according to that, could, in theory, solve almost do anything, could do arbitrary computations. Very important idea, and he was able to use that to learn a lot about mathematical logic. And this is called the Turing Machine. No one would ever build a computer like this, but you want every computer to be able to do arbitrary computations, and that's what's called being Turing complete. So really, really important in the theoretical understanding of computers. But that didn't lead to the modern computer in the sense that we know it. The person that really pioneered that came a bit later, and he's a real hero of mine, John von Neumann. Now, if anyone can claim to be kind of a polymath in the whole of mathematics, it's von Neumann. Von Neumann worked in everything. He worked in the purest of pure maths. He worked on problems as applied as bubbles in beer. He looked at shock waves. He was one of the founders of what we call game theory. We probably would have won the Nobel Prize for Economics if he'd lived a bit longer. He made profound progress in mathematical set theory, in analysis, in algebra. He also worked heavily during the Second World War on the atomic bomb. He could compute in his head faster than most people could compute using any electronic device, and he invented the computer as well. So quite an amazing guy. He didn't live terribly long. He sadly died of cancer at the age of 54. But if there's any mathematician that I admire most, it's von Neumann. And again, you can learn more about him in one of Ray Flood's lectures. So he worked on the computer, developing electronic computers during the war for the bomb. But later on, he worked on development of bigger computers. In fact, one of the first big jobs he did after the war was develop computers to do weather and climate forecasts. And he did a lot of work on how carbon dioxide affects the climate. So he was well ahead of his time there. And this little thing here is a kind of note he wrote. The story is that he wrote it whilst commuting between Los Angeles and San Francisco on the train. And this is called the first draft of a report on the EDVAC. EDVAC was the computer that they were developing at the time. And it was in this that he laid the framework for the modern electronic computer. And the modern electronic computer has what's called a von Neumann architecture. And a von Neumann architecture has a memory unit, and an arithmetic unit where you do all your computations, and a control unit which does all the stuff of controlling everything else, input and output. And that is the architecture that's in every computer that you've got. So that's the basis of your laptop. So when I was at school, again, I was using computers based on this. The arithmetic unit and the control unit together were about the size of a filing cabinet. And the memory unit was lots of tapes whirring around. Nowadays, that would be a tiny fraction of an inch on a chip. Okay, so things have changed a lot. So that's the von Neumann architecture, the basis of the modern computer. And one of the computers that led on from this was called EDSAC, which was the computer at Cambridge in the 1940s. When I was a student at Cambridge, many of my lecturers had grown up on this machine and said that the first thing that they had to learn when using this machine was where the fire bucket was, because they're all based on valves and it would catch fire at an alarming rate. But it was based on valves. It had about a kilobyte of memory. A kilobyte, compare that with what we've got nowadays. It could do just under 1,000 instructions a second and 18 operation codes. But it was way, way ahead of anything else at the time. And that's, let's say, one of the first computers that was used by general people. So that was used by ordinary lecturers at Cambridge. Here's a nice quote, 1949. The brain may one day come down to our level of common people with the help of income tax and bookkeeping calculations, but this is speculation, and there's no sign of it so far. So that was 1949. Things have changed a bit since. Here's just a self-indulgent slide. When I was at school, these were the computers that I grew up with. Susie on the left, which was my school computer, and 1975, not bad, and PDP-10, which was the computer at the Hatfield Polytechnic. And I'm sufficiently sad that instead of doing normal things on a Saturday, I used to get on my bike, literally cycle to Hatfield Polytechnic, now the University of Hertfordshire, and spend a happy day programming this and come back in the evening. Instead of going to parties and things that normal people would do. But that's what I did. Okay. So that kind of brings us up to date. But it's fair to say that the other big change that's also brought us up to date, I've talked a lot about hardware, has also been a change in the way we program And early computers, including the one I programmed at school, you program them in machine code. So you program in lots of numbers, which are really quite awkward. And then languages like Fortran, COBOL, and Pascal came along a bit later, which allowed you to program in something a bit more like English, and BASIC, and C. And modern languages are constantly evolving to do ever more sophisticated tasks, and these are all basically based on mathematical logical ideas. Okay, so that kind of brings us up to date. So I want to tell you now a bit about scientific computing. And this is going to be a bit self-indulgent because this is very much my own field of work. And you can see why I've got into this, given my strange history of cycling to Hatfield Polytechnic on Saturday mornings. Okay, so my own field of work is scientific computing, and what that means is that I work in developing algorithms to solve problems based in strictly scientific terms. So what does that mean? That means problems in physics, chemistry, biology, neuroscience, cosmology, climate science, big area of mine. Also engineering, so if you fly in an aeroplane, that would have been designed by a scientific computer. If you drive in a car, that was designed by a scientific computer. The first car to be designed by a scientific computer was the E-type Jaguar. So that's not a bad car. It's used by the drug industry and many other things. Scientific computers are also used a lot in the film industry to do our animations, and also in gaming. And some of the biggest calculations currently being undertaken at the moment are scientific. What do I mean by big? Sheer volume of computation. So a climate computation. When I do a climate computation, I'm typically solving problems with many, many billions of unknowns and doing calculations as quickly as I possibly can on those. And the heart of scientific computing, the mathematical heart of scientific computing, is a branch of maths called numerical analysis. And that is the maths that's used to design algorithms to solve scientific problems accurately and efficiently. So I have already told you about Turing. There are a number of biographies of Turing available. And I remember reading one, and it said Turing at this point decided to study numerical analysis. And there was an asterisk. And at the bottom of the page, after asterisk, it said numerical analysis is a branch of mathematics regarded by most mathematicians as even more boring than statistics. Okay, so that's my field. So numerical analysis is the business of solving mathematical problems. And it has to do a number of things. One is the challenge that Babbage raised of how do you represent numbers and add them up as accurately as possible whilst not taking a long time over it. Anyone that used the Sinclair Scientific, which had a decimal, could store 3 decimal digits. That's one of the first scientific computers. Calculators will know that that was a problem. Modern computers typically work with about 20 decimal digits. These are the sort of problems that I have to develop algorithms for my own work. This is what's called an ordinary differential equation, which governs how things evolve in time. This is a partial differential equation, which tells you how things evolve in time and space. And this is a matrix eigenvalue problem where you're trying to find x and lambda to solve this. And if you think, well, what's the point of doing that? That's what Google does every day to, whenever you type, if you Google Gresham, it's actually solving that equation to find all the information you need. So these are the sort of core problems that we're trying to solve using the sort of techniques which I devise. Why might I be interested in solving them? Well, again, I want to tell a sort of slightly historical story, and which also illustrates the point at the same time. So after my various kind of cycling trips to Hatfield Polytechnic, I eventually became a PhD student at Oxford, working in the area of scientific computing. And in 1987, I was due to go to Scotland and to catch a train from King's Cross. And I went down to London to catch the train, and I couldn't get into the station because there was a huge fire going on in 1987, which was quite a, impacted me quite a lot. If I'd turned up an hour earlier, I would have been in that fire. What happened in 1987 was that somebody dropped a cigarette on an escalator. That started a small fire, and no one worried about it too much because they thought they had it under control. And then suddenly the small fire turned into a huge fire, which went up the escalator, got into the ticket hall here, and killed really quite a large number. Something like 40 people died. And if you go to King's Cross, you can see a plaque to them. So that affected me very deeply at the time. As I said, I was only an hour away from being in that fire. But then it affected me later on because I got involved in the investigation to see what happened in that fire, which required a computer simulation, which was done at Harwell, and my project at the time involved working with the people at Harwell. So I'm going to talk about this much more in January, but the idea behind the investigation was to use the process of what's called mathematical modeling, which is where you take a real system, you make a model, which is a sort of mathematical simplification. As I say, I'll talk about this much more in January. And then you perform simulations on that using a computer. You get the results from the simulation, and you compare them with experiments to try to give you insight into what happens. Okay, this is quite a complicated process. I'll talk about it in detail in January. By the way, that's the lecture on how math saves the whales and cures cancer. So, slightly ambitious lecture. But anyway, you'll see. So that's the process that we're doing, and that's what we did for King's Cross. And what you do when you do a simulation on a computer is you typically take a problem and you break it up into lots and lots of smaller problems. So if I'm trying to, say, do the climate, I might break the Earth into lots and lots of little cubes, and then you solve the climate on one of those cubes, or what we call a finite volume, and then you put it back together to get the whole of the system. That's how a simulation works. And that's what we do all the time if we're modeling the weather or climate. This is the breakup. King's Cross, here's the ticket hall. And here is the escalator going down into where the trains are. And the fire started off here, and they broke the ticket hall and the escalator up into all these volumes. I hope you can kind of see how that's being done here. And they wrote down the equations for the fire, which are basically the equations of fluid motion and combustion. And then they solved these on the computer. I'll show you the computer in a minute that they solved it on. And what the model predicted was that the escalator here acted like a chimney. And the fire heated the air up here. The air went up the escalator. It acted like a chimney and pushed the fire up. An effect called the trench effect now, which was discovered purely as a result of the computation. The computation found that result, and then they went off to do some experiments and they confirmed it. And that showed to me the sheer power of computing, that you could, by doing a model and a scientific computation, actually discover something which wasn't known before, and that helped explain why so many people died and led to a large number of reforms to the way things were done in the tube, including banning smoking. That's the computer it was done on. That was the Cray 2, which was at the time the very first supercomputer. This was a press cutting from 1987. Here are two genuine Harwell people with genuine 80s haircuts. Okay. If you compare this to a laptop, nowadays it could do 1.7 gigaflops, that's 1.7 billion calculations a second, and had 2 billion bytes of RAM. Any laptop now would, blow that away. So that was tiny compared with a laptop, but it was pretty damn good at the time. And this was the cooling system, which glowed blue. It was wonderful. So that was the Cray 2, and that was one of the first ever supercomputers. Things have come on quite a long way, but I want to tell you this is a lecture on the mathematics of future computing. This is a somewhat technical slide, but it shows you what we're up against. The way you do these calculations is that you divide the place up, the ticket hall or whatever, into these what we call finite volumes. If you take n in each direction in 3 dimensions, you get n cubed volumes. You have to have n large to get higher accuracy. The accuracy decreases like 1 over n squared, but the time it takes to do the calculations increases like n to the 6th. These are fundamental numbers. It's really hard to get round. And so if I want to increase my accuracy by a factor of 4, that means I'm going to spend 64 times more time calculating that. And if n is big, say 10,000, these become very, very big numbers. Or it can take literally months to do these sort of calculations. And that's why we need supercomputers, because computation time goes up very rapidly as you increase accuracy. So in a climate forecast, well, let's take a weather forecast. If I want to increase the resolution from 2 kilometers to 1 kilometer, which is not unreasonable, then I'm talking probably taking 50 times longer to do that calculation. So that's why we need supercomputers, and that's the maths of computer, as far as I'm concerned. The other thing is to try to get this number down, and that's where I very much involved. If I can get that 6 down to a 4, then I'm making a big difference. Okay, so supercomputers, which I want to talk about for a bit, have sped up basically due to 2 reasons. One is the increased amount of hardware. So as I say, Moore's law means that we can put more and more transistors on a chip, but we're coming to the limit of how many we can put on a chip for 2 reasons. One is the quantum effects. So as things get smaller, so quantum effects get bigger, you get randomness coming in because of that. So we may be getting to the limit of how many transistors we can put on a chip. And the other is heat. So the more transistors you have on a chip, the hotter they get, and the more power they need. So a modern supercomputer, the Met Office computer, needs megawatts to run it. Megawatts. And that means a climate change computer, a computer to calculate climate change, is contributing significantly to global warming. Okay, and this is a big problem, and it's again a big area of research. Can we make the algorithms more efficient? Can we get away with simpler things to cut this down on? But that's really a kind of area where we're seeing problems, but this is what we've got to solve if we're going to compute better in the future. The second is what I call the Red Queen's race of software. You might notice every time you get a computer, it runs slower than the one you had before. You may not notice it, but they tend to. And the reason is that software companies develop better and better software, and it's more and more sophisticated, and the hardware isn't keeping up with it. And so it can be difficult to get software to run fast, the more sophisticated it gets. But another area where we are making a lot of speeds up is in what we call parallel computing, which is the business of doing lots of calculations at the same time. So if I want to do a parallel computation, for example, I could use everyone in the same room to do one calculation. And that means I can do, looking at you, there's probably about 100 in the room or so, 100 calculations in one go. That's called a parallel computation. And modern computers do a lot of calculations all at the same time. So the Met Office computer does 460,000 computations all at once, and that's called a parallel computation. And that will speed things up, but it won't speed it up 460,000 times, because if someone at the front does a calculation, someone at the back might need the result of that calculation, so they have to get off, run all the way to the back and get to the back, and then run all the way back again, and that takes time, and that's what we call message passing. And again, that slows things down, and that's another problem where we're trying to do research to speed things up. Okay, I put a calculation in the notes. I haven't got time for it now, but if you want to go into the notes and have a look, it'll tell you a bit about how that all works. Okay, but all of these things are helping, and we're getting to speeds of computers which would have kind of been undreamt of in the times of von Neumann and all that lot. And we're up to what we call petascale computing now. This lovely thing here is a petascale computer called Jaguar, which is at the Oak Ridge National Park in the US. What's a petascale computer? Here's the magic number, 10 to the 15. That's one with 15 zeros after it, which is 1,000 trillion. The Met Office computers are petascale computers. They can do 14 times 10 to the 15 arithmetic operations every second. Let's compare that with the EDSAC at Cambridge that could do 1,000 a second. And my first computers I was using at school were about that speed. That's an incredible speed. 10 1,000 trillion calculations a second, and they can store all those numbers in memory. And so that's where we are at the moment. The first one went online in 2008. There are about 20 of these around at the moment. Many of them are used in climate and weather forecasting, but they're used in other things, such as cosmology, genomics, molecular dynamics, drug design, all these sort of areas. There's also ones that are in use for naughty things, which I'm not able to tell you about because no one tells me about what they're doing, but they're behind people on barbed wire fences and stuff like that. But this is what we can now do, and scientific computing is a hugely important area. It's by far our best bet for knowing what's going to happen to the planet for climate change. That's a Petascale computation, looking at the way that the oceans are warming and the clouds are forming over it. And so the calculations I do with the Met Office, again, are using all these sort of things. If you want to know what the ocean looks like, that's a simulation of the ocean using a Petascale computer. It's beautiful stuff. And sadly, I can't show you it swirling around. That's beyond my bandwidth for this talk, but you can go and look these things up if you want to. That's a simulation of brain activity on a Petascale computer. And this is my favorite of all. That may look like what you get if you look at a telescope at the sky. No, that is a simulation of a galaxy forming using a Petascale computer. And looking really, really good. And we're up to the point where we're going to see exascale computing. That's 1,000 times faster. We have our first exascale computer that's done that calculation. It's been done once on a genomic calculation, but China is planning a ton of these in years to come. And zetascale computing, which will be 1,000 times faster than that, is estimated to occur in 2030. Watch this space. There's an article in the Times today bemoaning the fact that due to Brexit, investment of the UK of supercomputers has essentially stopped for a while, which is a bit of a worry because we might well be taken over by these guys. I just wanted to very quickly, because I've covered this in other talks, say that whilst supercomputing is something I'm very passionate about and will affect our lives in many ways, what's probably going to affect our lives even more is what's called machine learning. And you can go back and look at my previous talks on this. So computers are impacting our lives through things like Google, mobile phones and credit cards and so on. But a tsunami is about to hit us. And what's the tsunami? The tsunami is deep learning, where you can get computers to learn how to do things. This is a computer here. It's what's called a convolutional neural net, which is used for face recognitions. This is what things like Facebook and so on are using as face recognition, or the police and so on. And machine learning has many other applications, fairly benign, things like playing chess, looking at our face, recommending books for us on Amazon. But some are more worrying things like replacing doctors for medical diagnosis. I'm afraid this is an area I work in myself. Recruiting people for companies, dating websites, driverless cars, and replacing judges. So we have to ask ourselves the question, do we want a future where computers are doctors, car drivers, and judges? Okay. I'm not going to say very much in this lecture. If you want to have a read about this, go back to my lecture, Is a Mathematician a Robot?, which will tell you much more about machine learning, and I'll also touch on it in future lectures. But this is a big thing that's going to hit us very hard and is largely based on the computing ideas that I've described earlier. So there we are. There's our doctor on the left. I've run out of time, but just to say the other big development that's going to hit us possibly is quantum computing, where we use the full power of quantum mechanics, again, to speed up the way we do computations very, very radically. And if you want to read about that, my lecture is the quantum mathematician will tell you all about that. So I'll just whiz through that. So I'm going to just get on to my last slide, which is to say that I've shown you the way computing is going. and the way I think that mathematics is doing this. And certainly exciting times lay in front of us, but we have to watch it to make sure we're not complacent. So John von Neumann, who, as I say, was the mathematician I hold in highest regard of all mathematicians, famously put his foot in it, well, sort of put his foot in it when he said this: it would appear we have reached, this was in 1949, the limits of what is possible to achieve with modern computer technology, although he saved himself. One should be careful with such statements, as they tend to sound pretty silly in 5 years' time. I'd love to think what von Neumann would think if he was around today. Thank you very much.